Hello, everybody. We're Team 7. I'm Reese Maiden.
I'm David Wilson.
And I'm Jackson Peterson.
And today we're going to present our findings on accidents and injury severity. So to get into our business understanding, we just kind of want to make a foundation for the importance of the overall project and the data. So traffic accidents and resulting injury severity analysis are crucial for uh, any sort of government, state, local, or federal, transportation authorities, automotive manufacturers, and the general public. Understanding the factors that contribute to injury severity aids in accident prevention as we can develop targeted strategies to minimize negative outcomes, saving lives, and reducing economic burden on members associated with road accidents. In the United States, there are over 30,000 fatalities and 2 million injuries per year as a result of automotive accidents, which cost the economy over $230 billion annually. The objective of this study is to leverage advanced analytics and machine learning to analyze historical crash data and identify influential factors contributing to injury severity, as well as develop predictive models that can help predict the severity of injuries and accidents. We've got two main goals for this study. The first is to develop accurate predictive models with in regards to injury severity levels based on various risk factors associated with crashes. And then the second goal is sensitivity analysis to help determine the relative importance of specific risk factors across different injury severity levels. Our expected outcomes are to enhance the understanding of automobile accident dynamics and inform the development of targeted strategies and policies for improving road safety. And we're going to do this by employing machine learning techniques and sensitivity analysis to determine the most important factors and then use those factors to develop those targeted strategies or campaigns. We have four data sets in this study: the vehicle data set, accident data set, person data set, and distract data set. The vehicle, kind of self-explanatory, relates to the factors of a vehicle, such as make, model, year, or gross vehicle weight rating. The accident data set is specific to the accident, so it has month, day of crash, conditions, or relation to junctions, or if it's on a highway or not. The person data set covers information regarding the individuals in the incident or accident. Examples of the variables include age, sex, restraint system usage, or airbag deployment. And then the final distract data set just is one variable, and it consists of distractions experienced during or shortly before an incident. For data processing, we're given the four data sets, which comprise of 141 total variables. So condensing this information is the first task that we have. And this is done by reviewing the data dictionary to analyze and stratify the variables based on perceived relevance. We first eliminate irrelevant variables, getting rid of like trivial data points such as like school bus involvement or minute data, which are likely to contribute very minimally toward the understanding of crash dynamics. And then we also excluded cheating variables, which are variables that are linked to the prediction variable, such as maximum injury severity or hospital. These are excluded in favor of retaining variables like drugs, airbag, or rest use, which are likely to have a significant prediction value or impact. Slide, please. So for this project, we are using KNIME as our sole software system for data preparation, data cleaning, as well as model building. The first steps in KNIME that were taken are to load in the provided data sets and join them. You can see in the image below that the orange nodes are the SAS readers, which the initial data was in a SAS file. So this reads in the SAS data files and converts it to a uniform table that KNIME is able to recognize and use. And then the yellow nodes are used to join the 4 data sets into one single data set with all of the variables to help us perform analysis. Slide, please. The next step of data preparation involves creating the dependent variable, which we named injury severity. We do this by utilizing the seat position and body type variables. The initial node generates a uniform dependent variable, which focuses solely on the driver's seat position. We do this to create uniformity in our prediction model, as different seat positions could drive different injury severity outcomes depending on the type of accident. So for this study, we're only going to focus on the drivers. The second node filters out the non-standard vehicle types. So any type of vehicle that has an atypical configuration, like a dump truck, construction vehicle, anything that's kind of out of the ordinary, not standard, like a box truck, etc. This helps us, refine our dependent variable and cleans up our data set to avoid using statistically different vehicle types, which could have different injury outcomes. The final 2 nodes are used to clean the dependent variable further. We discard values greater than 4, which represent incidents with no injury or unknown injury. And then the final node categorizes the 4 remaining categories into 2. 1 and 2 are categorized as low injury, which categories 1 and 2 were originally possible or suspected minor injury, and then 3 and 4, which were originally suspected serious injury or fatal injury, are now categorized as high inj. Slide, please. The next step of data preparation is the column filter. So the table that I referenced earlier when it came to cleaning the data set based on the data dictionary, eliminating the cheating variables, as well as the insignificant variables. This column filter is what we use to actually clean the data set in KNIME. The benefits of this are streamlining the model and the data set, which reduces computational complexity and completion times for our models. It also increases prediction accuracy and enhances metrics like sensitivity and specificity. Slide, please.
After selecting our 34 columns, we transform the data a little bit more. We use rule engines to filter out missing values, converting them to null values. And then we did some more transformation on those variables by moving strings to number and numbers to strings, so that we can ensure consistency in our data types across the data set. Then we put it through a missing value node to replace null values with mean and median values for numeric and categorical data. We also created a new variable that was to determine if the person was going over the speed limit or under the speed limit. And then finally, we grouped those variables into less than 5 per column to help support the neural network and support vector machines. Next slide, please. Moving into the models, we used 8 models. 5 of them were set-based, and 3 of them were numeric. Next slide, please. Our first model was the decision tree. We use a tenfold cross-validation gain ratio, and then did the MDL pruning to help eliminate to remove sections of the tree that were not impactful. This resulted in a 72% accuracy. Next slide. Next, we use a gradient boosted tree. We also use a tenfold cross-validation. We surrogate missing value handling binary splits for nominal variables and midpoint splits for numeric variables. This resulted in a 74% accuracy. Next, we used a random forest model. Again, tenfold cross-validation, use a Gini index split with unlimited tree depth. This resulted in a 75% accuracy. Next, we did a neural network. We normalized the overspeed variable using a tenfold cross-validation with 10 hidden layers and 100 hidden neurons per layer with 73% accuracy. Next, we did a logistics regression model. We also normalized the overspeed variable with a -1 min-max, again, using tenfold cross-validation, reweighting the least square solver, and this resulted in a 73% accuracy.
We also prepared an XG boosted trees model. Key properties on that model were tenfold cross-validation, like those before, a binary logistic objective, 100 boosting rounds, and a base score of 0.5. This model produced a predictive accuracy of 71%. We created a naive Bayes model. It uses a normalizer node with, like before, -1 to 1 min-max normalization, incorporates tenfold cross-validation. The learner is configured for a max of 8 unique nominal values per attribute, since our largest categorical variable contained 8 values. We did the best we could to keep under 5 per variable. We had one category that wasn't possible. But that model produced a 74.8% predictive accuracy. We also created a support vector machine. It uses the normalizer like before on the overspeed variable with -1 to 1 min-max normalization. We do one-hot encoding on categorical variables using the one-to-many node. We incorporate tenfold cross-validation, and the support vector machine learner uses the hypertangent kernel, a kappa of 0.1 and delta of 0.5. It produced a 18.9% accuracy. We created 2 separate sort of analyses for variable importance. The first, we used the random forest weighted sum method, where we assign a weight to each of the 3 top layers, with the first weight being 1, the second weight being for the second layer being 0.1, and the weight for the third layer being 0.01. And with this model, we take the results from that variable importance calculation, and we compared it to the output from a logistic regression coefficient analysis. Using the logistic regression learner, the coefficient output, we were able to produce a model shown in this slide. On the left, we see the random forest variable importance shows ejection, restraint use, occurrence of a fire during a crash, restraint misuse, and accident type as the top 5 most significant variables. On the right-hand side, we have logistic regression, the coefficient analysis from the logistic regression model. And interestingly, we see 4 out of our top 5 from the variable importance with random forest in our logistic regression top 12. We can see ejection equals totally ejected as the highest coefficient. Accident type equals same traffic way, opposite direction as the number 2. A little bit further down the list, occurrence of a fire in the vehicle, yes, is 9.8, and restraint use at number 12. restraint system not used. So kind of gives us some validation that our random forest variable importance is accurate. The results from all of our models are compiled in a composite table and ROC curve on this slide. Our decision tree, 72% accuracy, gradient boosted tree, 74, random forest, 75, neural network, 73, logistic regression, 73, XGBoost, 71, naive Bayes, 74, and support vector machine, 18. Even though the random forest model produced the highest accuracy, the XGBoost model has the lowest spread between sensitivity and specificity. We felt that due to the nature of the data set, that a small spread in sensitivity and specificity is as important as a few extra percent points on predictive accuracy due to the low number of occurrences in the positive class. The ROC curve shows an area under curve in the high 70s for all but our support vector machine model. Takeaways from our study. We believe we're able to develop some targeted strategies for reducing the likelihood of severe injuries for drivers. The largest one is kind of tackling preventable injuries, right? With the promotion of seatbelt usage and restraint systems, we thought we would be able to make an impactful change in high severity injury occurrences with implementing educational campaigns and awareness programs for driver and passenger awareness of safety belts, proper use of restraint systems, and collaborate with government agencies, law enforcement, community organizations to promote safe driving practices. Number two, we think we can operationalize the results of our study with the enhancement of vehicle safety features, try to implement measures to prevent ejections during crashes. Obviously a big factor in injury severity in an accident. Staying in the vehicle, you have a lot lower chance of having a high severity injury. Also strengthening regulations and standards for vehicle safety, focusing on mitigating risk of fire occurrences, and investing in research and development for advanced safety technologies inside of vehicles. Number three is policy decisions and infrastructure improvements, utilizing data-driven insights to inform policy and to steer infrastructure improvements, optimizing road designs, traffic management systems, and enhancing signage and road markings to improve driver awareness. And finally, collaborative efforts take the results of our study to foster collaboration among stakeholders, government agencies, law enforcement, automobile manufacturers, and citizens, community organizations. Try to establish partnerships that implement and monitor the effectiveness of these targeted strategies and encourage ongoing evaluation and refinement of initiatives to ensure continuous improvement in road safety. In conclusion, in this study, we leveraged the CRISP-DM process. We developed a business understanding of the underlying accident data. We developed a data understanding in that data. We prepared the data for modeling with pre-processing, feature selection, and data handling. We built predictive models to predict injury severity and understand variable importance. We tested and evaluated those models, and we made recommendations for deployment of results of those models. We appreciate everybody's time and hope everybody has a great day. Thank you.